Okay, so I need you to sit with me for a second because what Huawei just pulled off is genuinely one of the wildest things I've seen in the chip world in years. For about 50 years, the entire tech industry has been chasing one goal: make transistors smaller. Smaller, smaller, smaller. And Huawei then just stood up on a stage in Shanghai and basically said, yeah, we're not doing that anymore. We've got a better idea. And the crazy part, they've already shipped 381 chips proving it works. So let's get into it because this might be the start of a whole new era of computing, and I think it's a bigger deal than most people realize. Let me set the stage for you. You've probably heard of Moore's Law. It's that famous prediction that the number of transistors on a chip roughly doubles every couple of years. That single idea is basically why the phone in your pocket is more powerful than computers that put humans on the moon. For decades, it just kept working. But here's the thing that nobody in the industry likes to say out loud at parties. Moore's Law is running into a brick wall. We're now building transistors so tiny that they're bumping up against the actual physics of atoms. You literally cannot keep shrinking things forever because at some point the wires get so thin and so close together that signals start leaking, heat piles up, and the costs go absolutely nuclear. The machines that print these chips, the EUV lithography systems, cost hundreds of millions of dollars each. And here's the kicker for Huawei specifically. Because of the US export restrictions, they can't even buy the most advanced ones. So they were stuck. Either give up on cutting edge chips or find another road entirely. And friend, they found another road. At the IEEE International Symposium on Circuits and Systems in May 2026, Huawei's He Tingbo gave a keynote called New Semiconductor Path and Practice, and she introduced something called Tau scaling law. Some folks in the industry are already nicknaming it Her's Law, which is, I think, a pretty nice touch, especially today. Now, here's the core idea, and I want you to really get into this because it's beautiful in its simplicity. For 50 years, we've been obsessing with one question: how small can we make a transistor? Huawei flipped it. Their next question is, how fast can we move information through the whole system? That is the tau part, the Greek letter tau. In electronics, tau represents a time constant. It's basically how long it takes a signal to travel and settle. The formula is tau equals R times C, resistance multiplied by capacitance. And the genius move here is that you don't have to shrink the transistor to lower that number. You make the wires shorter. You cut down both the resistance and capacitance at the same time, and the signal gets where it's going faster. Same factory, same manufacturing process, dramatically better performance. That's the whole bet, and honestly, I love how elegant it is. So, how do you actually shorten those signal paths everywhere? This is where it gets really cool. Huawei built what's essentially a 4-level optimization framework, and you'll hear it called the 4 foldings, that attacks the time constant at every single layer of computing. Let me walk you through all 4 because each one builds on the last. Level 1 is the device level. This is the most basic level, tuning the actual transistor and their immediate connections to cut down resistance and the parasitic capacitance that slows everything down at the physical level. Level 2 is the circuit level, and this is where the star of the show lives, LogicFolding. We'll dig into this one in a second because this is the headline act. Level 3 is the chip level. Here, Huawei coordinates the software, the architecture, and the silicon all together, so data and instructions flow through the chip with way less wasted time. And level 4 is the system level, where they connect thousands of chips together so a giant cluster behaves like one single brain. This is where the UnifiedBus tech comes in, and trust me, the numbers here are bonkers. What I find genuinely clever is the Tao becomes this one shared language. A transistor engineer, a circuit designer, and a data center architect can now all talk in the exact same metric. The whole time scale they're optimizing across spans something like 12 orders of magnitude, from picosecond transistor switching all the way up to system-wide response time. Nobody had unified all of that under one target since the Denard scaling era, and that's a real intellectual achievement, and not just marketing. Alright, the main event, logic folding. Here's the easiest way I found to picture it. Imagine a giant single-story office building. If somebody on one end needs to hand a file to somebody on the far end, they've got a long walk across the whole floor. The walk is wasted time. Now, instead, picture folding that building into 2 floors and dropping a staircase right in the middle. Suddenly, the trip is a fraction of the distance. That's logic folding. Instead of laying all the logic circuits out flat on a single 2D plane, Huawei folds and stacks them into multiple vertical layers. Some people described it like printing 2 chips, then folding them together like a taco so they line face to face. And the way you connect those folded layers through a packaging technique called hybrid bonding, basically fusing the copper contacts of 2 chips directly together with no bulky middleman. Huawei says they're hitting a bonding pitch of around 1.5 micrometers, which is extremely fine. A single that used to travel hundreds of micrometers sideways across a flat chip can now just shoot straight up or down a tiny vertical path measured in tens of micrometers. Shorter wire, lower R, lower C, smaller tau, faster chip. And the cherry on top, stacking the logic vertically also means you cram more transistors into the same footprint without ever needing a smaller manufacturing node. They start with a 2-layer design now and have a 3-layer version on the roadmap. It's so simple in concept, it almost feels like cheating, and I mean that as a compliment. Now, I know what you're thinking. Cool theory, but does it actually work? And this is the part that made me sit up. This isn't a research paper sitting in a drawer. It's upcoming Kirin 2026 chip, the one going into the Huawei Mate 90 this fall. Transistor density reportedly jumped from around 150 million transistors per square millimeter to about 238 million. That is a 55% increase. They're also claiming 41% boost in power efficiency and roughly 13% higher clock frequency. And get this, Huawei says clock speeds on their new chip are finally competitive again for the first time since they lost access to advanced fabs. They literally clawed their way back without the forbidden machines. Industry watchers estimate this folding approach delivered a density jump equivalent to about 3 years of traditional scaling in one single move on already existing equipment. And the long game? Huawei is projecting transistor density equivalent to 1.4 nanometer process by 2031. That's a wild ambition, and even if they only get part of the way there, it reshapes the conversation completely. Now let's zoom all the way out to that 4th fold, the system level, because this is where it stops being about phones and starts being about the AI arms race. Huawei's answer here is UnifiedBus, a new interconnected protocol that lets a massive pile of chips share memory and talk to each other almost as if they were one single processor. They claim it cuts the time data spends in transit by roughly 500-fold by stripping out all the layers of translation that normally slow chip-to-chip communication down. Here's the scale. The Atlas 950 SuperPoD wires together up to 8,192 chips, so they act as one logical computer with a shared memory pool, which is exactly what you need to train these monster AI models with trillions of parameters. And then you stack 64 of those SuperPoDs into what they call a super cluster, and now you're looking at get over 520,000 AI processors working together, pushing 524 exaflops. They've also got an optical interconnect tech called Huwaei that swaps out bulky copper cabling for high-speed light, which is the only way clusters that dense are even physically possible. Going from thousands of connected chips to over 500,000 acting as one, that's the kind of leap that genuinely keeps NVIDIA executives up at night. Now, I'm not just gonna hand you the hype with no reality check, because honestly, that's not what you're here for. The big challenge with folding and stacking logic vertically is heat. When you sandwich active circuits on top of each other, you're trapping thermal energy in a very tight space. And you can't exactly bolt a giant fan inside a phone. Managing that thermal sealing is the hard part, and it's the thing I'll be watching most closely when these chips actually ship. The other catch is the skeptics, and they make a very fair point. NVIDIA's Jensen Huang responded to all this by basically saying, yeah, stacking and hybrid bonding is real, it's a good technology, you can multiply your transistors that way, but TSMC has been doing advanced packaging like this for nearly a decade. So the debate is if Huawei invented something brand new or cleverly repackaged techniques the West already had, and TSMC and Intel still hold a real lead on raw process nodes. Here's where I land, honestly, and I'd love to know if you agree, by the way. Whether or not tau scaling fully replaces Moore's law, I think Huawei did something important. They reminded the entire industry that there's more than one way to make a computer faster. When one door slammed shut, they didn't quit. They found a window nobody else was looking at, and they shipped the real product through it. And that is kind of motivating and very good to hear, because the way things are going right now, we're really running out of options when it comes down to development and evolution of AI chips.